So, we are dealing with the flow through a circular tube in which there is an imposed pressure gradient and gravity is also present. So, our goal is to obtain the velocity distribution inside the pipe during the flow and to obtain an expression for the volumetric flow rate. Now, this volumetric flow rate, based on our understanding so far, we realize that it will contain some geometric parameters. For example, what is going to be the length of the pipe, what is its radius. There will be some operational parameters. For example, what is the pressure difference that we have imposed from outside, that is what is P0 minus PL, or what is the value of P0 and PL. It should also contain a description of the force field, body force field which is present. In this case, it is gravity, and since it is vertical, it is simply going to be G. The geometric and the operational parameters, namely R, L, P0, PL and gravity, all these would be connected with the velocity or with the flow rate by another physical parameter, a physical property. And the physical property, or more correctly the transport property in question in this case, would be viscosity. So, whatever expression of velocity or volumetric flow rate that we would get should contain all this. So, we have done this analysis and we have come up with the governing equation. Now, this governing equation has to be solved with appropriate boundary conditions. So, let us start with our final form of the governing equation and see what we can do in order to obtain an expression for the velocity. So, what you have in here is this expression that we have obtained for this. If you integrate it twice, what you are going to get is the expression that you are going to get out of this is from this one. Once you integrate this, it would be P0 minus PL by 2L R square plus C1, or in other words, I can express it as tau Rz is P0 minus PL by 2L times R square R plus C1 by R. Now, we realize that this gives us an opportunity to say something about the value of the integration constant C1. We understand that tau Rz must be finite at R equals 0. Shear stress cannot be shear stress has to be finite at R equals 0, and this can only happen if C1 is 0. So, the fundamental condition that the shear stress cannot be indefinite at any point in the flow field will give me the expression, will give me a definitive value for one of the boundary conditions. So, in certain cases, the physics of the problem has to be kept in mind, not just blindly no slip and no shear at two interfaces. In some cases, you can make a definitive statement about the nature of the velocity, nature of the flow, nature of shear stress, which would give you an additional physical boundary condition, which in this case we have used to obtain the first integration constant C1. So, once we know C1 equals 0, then the remaining part of the equation can be integrated to obtain what is the velocity distribution. So, that is what let us see what we do that in. So, your expression, once you do the integration from that point onwards, that is your tau Rz would simply now become P0 minus PL by twice L times R, and use Newton's law of viscosity. So, your tau Rz is minus mu times dVz dr. So, when you plug this in here, what you have is then dVz by dr is equal to minus P0 minus PL by 2 mu L times R, and upon integration it would give you Vz equals minus so C2 is the the second integration constant. Now, how do you evaluate C2? You need a boundary condition, and the boundary condition that is available to you is no slip at small r equals capital R, because in this shell when small r becomes capital R, then you essentially have a liquid solid interface, and at a liquid solid interface the relative velocity is 0. So, you would have Vz equals 0 at small r equals capital R. So, that is the second boundary condition which one can use to obtain the expression of velocity, final expression of velocity as Vz equals P0 minus PL by 4 mu L. In fact, this should be 4 mu L R square 1 minus R by R whole square. Okay. So, this is the expression of velocity which for flow in a circular pipe in presence of pressure gradient and gravity which is embedded into it, and all other parameters, the geometric parameters R and L, and the property, the transport property mu is already present in here. I would write it once again just to, because it would help us in our discussion, is Vz as P0 minus PL by 4 mu L times R square times 1 minus R by capital R whole square. So, operational parameter, geometric parameter, and the property of the fluid. And it is clear, it is obviously then the velocity distribution, because of the nature, because of its R dependence, the velocity is going to be parabolic in nature. So, this is your R and Z. So, velocity starts at a value equal to 0 due to no slip at the solid wall, reaches a maximum, and the variation is parabolic in nature. So, this is the point of maximum velocity, and from the expression you can simply write simply see Vz max is essentially at R equals 0 at this point, which would simply be equal to P0 minus PL by 4 mu L times R square. So, you can write Vz as Vz max times 1 minus R by R whole square. The expression for Vz can also be written in this way. But you are, as engineers, you are probably not interested in knowing what is the velocity. You are more interested to know what is the flow rate for such a case. When I apply a pressure gradient, when I have a gravity force acting on it in a pipe of known diameter and length, how much of fluid can I expect at the other end, or how much of fluid I can collect which is coming out of the tube per unit time. In order to do that, the first step is to obtain an expression for the average velocity, and to obtain the average velocity I need to integrate this velocity across some area. So, what area it should be? The flow is in the z direction, and I need, in order the average velocity, and it varies with r. So, the flow area which I need to incorporate in order to obtain the average velocity must be some area which is perpendicular to the flow. So, if I take the cross section of this circle, then the circular area must be the flow area across which I need to integrate in order to obtain an average velocity. So, all velocities are area average velocities, and all these areas are always perpendicular to the direction of flow. So, it is this area integration from 0 to 2 pi, from 0 to theta, then I have r dr d theta. That is the area, the cross sectional area which across which the velocity needs to be integrated. So, that is what we are going to do next. So, average velocity which is denoted by this sign, is simply equal to 0 to 2 pi 0 to r v z r dr d theta, and by the area which is 0 to 2 pi 0 to r dr d theta. This should be equal to P 0 minus P L by 8 mu L times r square, and in this is V z, and the V z is essentially this one from the previous relation that you plug it in here to obtain the expression for the average velocity. And once you have the average velocity, the flow rate q would be equal to pi r square times the velocity. So, this is meter square, this is has units of meter square, this is meter per second. So, this totally together it becomes meter cube per second, which is the volumetric flow rate, which would be equal to pi P 0 minus P L by 8 mu L times r to the power 4. This is a famous equation which is known as the Hagen Poiseuille equation. So, this Hagen Poiseuille equation gives you the volumetric flow rate for a fluid which is flowing through a vertical tube because of the presence of a pressure gradient and body force. So, this is the imposed condition, this is the geometry, these two are the geometries, and this is the thermophysical property or transport property. So, now you can make you can clearly see how we explain the principle of capillary viscometer. So, we measured the Q, the amount of liquid that you are collecting per unit time, and if it is falling freely vertically, then P 0 minus P L can be substituted just by the gravity force. You need to know the diameter or the radius of the capillary, the length is known. So, this you are going to find out experimentally. All these are known to you, the only unknown here is the property mu. So, using a capillary viscometer where a very thin capillary is used to obtain some flow out of the capillary, the only unknown being mu can be calculated. So, that is the principle of a capillary viscometer. Whenever we get such an expression, we need to be careful about what are the assumptions that we have made, because we need to know the assumptions in order to get an idea of the applicability, the region of applicability of any relation or a correlation that we have developed. The first assumption that we have made is that it is a laminar flow, straight streamline laminar flow. So, you cannot have a very high pressure gradient being applied to certain length of the pipe such that the flow inside gets disturbed and the flow becomes turbulent, does not remain laminar. If that is the case, this analysis will not be valid. This analysis also assumes that it is an incompressible fluid, that is rho is constant, the density of the fluid is a constant. So, this relation is restricted to incompressible fluid as well. So, incompressible straight streamline laminar flow are some of the constraints, some of the conditions which must be met before Hagen Poiseuille equation can be used to find out how the flow rate and the conditions are related by viscosity for such a case. But this is a simple yet elegant example of the use of shell momentum balance in everyday problem. And this Hagen Poiseuille equation has so many uses in everyday life, in physics, and in so many other cases. In order for the liquid column inside the pipe or tube to move with a constant velocity, we have assumed that sum of all forces acting on it must be equal to 0. Otherwise, if it is not the case, then the column of liquid which is flowing inside the tube will either accelerate or will slow down. Now, what are the forces which are acting on it? And we need, so physically we need to find out, think what are the forces which are acting on it. The liquid column is going down because it is acted upon by a difference in pressure, high pressure on this side and low pressure on this side, which is trying to pull it in this way. There is also a gravity which is trying to make the liquid column move in the plus z direction. So, these two, pressure and the gravity, are acting in the same direction. So, there must be an opposing force which is going to be equal to the combined effect of these two forces, equal and opposite. Only then it is going to move with a constant velocity. What is that opposing force? What is that force that opposes the motion of a liquid? There is no other way but the viscosity. So, viscosity is the one, the viscous force is the one which opposes any flow of the liquid imposed by some other conditions, pressure difference or maybe gravity. So, when you think of, if you try to find out what is the force which is acting on it, which is the opposing force that is making the liquid column move at a constant velocity, that must be the viscous force. And without solving anything, heuristically you should be able to say that the opposing viscous force is simply equal to the force due to pressure and the force due to gravity, which are acting on the column of the fluid. So, but in any case, if you would like to analytically find out what is the force that is acting on it, the gravity, you need to find out what's the viscous force at small r equals capital R, that means at the solid liquid interface along the inner wall of the pipe. So, what is that force? It's tau r z, the shear stress evaluated at small r equals capital R. So, tau r z evaluated at the inner wall of the tube, and this tau r z now has to be multiplied with the appropriate area, the area on which it is acting on. So, what is the area on which this wall shear is acting on? Must be equal to twice pi r times L. So, twice pi r L times tau r z evaluated at small r equals capital R is essentially the force, the viscous force that we are trying to find out. So, once you do the calculation, you would see that the shear that the viscous force is going to be equal to the combined force due to the pressure and the weight of the liquid column. So, this Hagen Poiseuille equation is something which we use every day, but you can get such a neat expression starting with the simple concept of shell momentum balance. So, what we are going to do now is we'll try to solve a few other problems using this simple concept of shell momentum balance. And towards the end of these exercises, we would slowly start to feel that it is getting increasingly difficult to use the shell momentum balance, because you need to visualize the complex geometries and those situations in which it is not a one dimensional flow. If you have flow in 2 dimensions, if you have velocity both in x and y directions, the shell momentum balance may not work, or it becomes too cumbersome. So, a generalized treatment, the need for a generalized treatment would become apparent as we start solving more and more difficult problems. But right now I'll show you one or two more examples of the shell momentum balance, and then do a conceptual problem which is also very interesting. So, let us now start with another problem, which is an industrial problem, in which case a belt, upward moving belt, so let us see that this is a belt which rises So, this is a liquid film, this is a liquid. Initially the belt is stationary, but let us say at some point the belt starts to move upwards with a velocity u naught. After you provide sufficient time, when it reaches steady state, the belt is going to have a thin film of liquid stuck to it. So, this is the liquid, this is your belt which moves with the velocity u naught, and you have given sufficient time such that this is the steady state which is reached. And let us say that this is my x direction, this is the y direction, and at some point when it reaches steady state, the thickness of the film is constant and it is equal to h. What we need to find out is, and you can see that you have V y in here, the V y is not equal to 0, V x is however equal to 0. There is no pressure gradient which is acting in this case, and only a force which is acting is gravity. So, the belt starts to move upwards and it will carry a thin film of liquid along with it, but the gravity would like to drain the liquid in the reverse direction. So, viscous forces pull the liquid up, gravitational forces tend to drain the liquid, and when a steady state is reached, let us assume that the thickness of the film is given by h. So, if that is the case, then we would like to find out what is going to be the velocity distribution V y in this case in the thin portion of the liquid. So, we have to think of a shell, and in order to think of a shell, we need to first identify what is the direction in which the velocity is varying, because whatever be that direction, that is going to be the smaller dimension of the control volume. You can clearly see that the velocity is varying with x. There is this is moving upwards, this is a free surface, the velocity does not vary with y, and there is no V x in here. So, in order to obtain the shell, if this is my wall and this is the liquid film and this is x and this is y, then my shell must be something which is of thickness delta x. It could be any length L, any width y, does not matter, because V y is not a function of y, it is not a function of z, it is only a function of x. So, that is why I am taking my shell as this. Okay. Now, when you consider this shell, then we understand that there is going to be, if I take this shell of delta x in thickness, and on this side I have the wall and on this side I have the free surface. So, some amount of momentum which is convective momentum will come in, some amount of the convective momentum will go out, but these two must be equal to each other because of my assumption that V y is not a function of y. So, whatever be the convective momentum here and convective momentum here, they must be equal and opposite. So, I do not need to write, when I write the momentum in minus out plus sum of all forces is equal to 0, and I identify that there is going to be a convective part and there is going to be a conductive part. The convection part I do not need to write, since the velocities at these 2 points are equal, but I need to take into account the tau. Now, what is going to be the subscript of tau? The subscript of tau, the first subscript would be the direction, the direction in which the motion is taking place. So, if you see this specific problem, the motion is upwards in the plus y direction. So, the first subscript of the shear stress in this case is simply going to be tau y. and as a result of motion in the upward direction and variation of in velocity, the momentum gets transported in the x direction. So, the subscript of tau would be tau x y in this case, y momentum gets transported in the x direction. So, tau x y is going to be this is going to be the shear stress. It is acting on an area, this is L and the width of this is W. So, it is acting on an area which is L times W, and this is evaluated at x. The out one is going to be tau x y multiplied by L and W again, evaluated at x plus delta x, and there is no body force which is acting on it, there is only gravity force. And in order to obtain gravity force, I first need to find out what is the volume of the liquid which is contained in the control volume, which is L W times delta x, mass when I multiply it with rho, and I put G in order to obtain the force, the gravitational force. But if you look at the coordinate system in here, I must put a minus sign in this case, since my G and Y are oppositely directed. So, convective momentum in minus convective momentum out, and then the gravitational force acting in the reverse direction, no pressure forces. At steady state, the sum of all this must be equal to 0. So, you see how easy it is now to write the difference equation. It is progressively becoming easier for you to clearly visualize the flow conditions, write the governing equation, get rid of all the terms which are not relevant. For example, in this case the transport of momentum by convection by flow, since the velocities are same at the bottom and at the top. So, no net contribution of momentum. The only contribution is the viscous transport in, viscous transport out, and the gravity which is acting in the reverse direction. So, the sum of algebraic sum of these three must be equal to 0, and that is what I have written in here. So, the next step is simply divide both sides by del x, take in the limit when, and obviously cancel L W from all side, divide both sides by del x and take in the limit when del x tends to 0. What you would get is dx of tau x y is equal to minus rho g. So, this becomes your governing equation right now. Okay. The momentum, so again this is the belt and this is the film. So, this is the liquid, this is the thickness of the liquid film, which is H. Now, this is air. So, the first thing that we can do is I can simply integrate it once to be equals minus rho g x plus C1. Now, at x equals h, tau x y must be equal to 0. X equal to h is the liquid vapor interface, and at liquid vapor interface the shear stress is 0. Since shear is 0 at this point, at x equals to h, tau x y would be equal to 0. So, your C1 would simply equals rho g h, and also tau, if I assume it is a Newtonian fluid, is simply going to be mu times dvy by dx, and this is dvy by dx, in using plugging this in here and using the value of C1 as rho g h, you can integrate this. I am leaving it for you to do. Vy would be u naught minus rho g h square by 2 mu times 2 x by h minus x by h whole square. This is the distribution that you should get. Now, you can see that it is slightly more complicated than the simple parabolic distribution profile. You have a linear term and you have a quadratic term, and you have the velocity with which the belt is being pulled up. The second boundary condition would be at x equal to 0, your v y must be equal to u. This is the very important boundary condition. At x equal to 0, that means at the liquid solid interface there is no relative velocity. So, all the molecules of the liquid which are here, they are moving up with the plate with the same velocity as u. So, at the liquid solid interface, the relative velocity is 0, which essentially I am talking, we call it as no slip velocity. Since it is no slip, the velocity must be equal to the velocity at x equal to 0 must be equal to the upward velocity of the belt. So, the belt pulls the liquid, the gravity tries to drain the liquid. A steady state is reached with the condition that the velocity on the belt on the liquid side would be equal to the upward velocity of the belt, which is no slip. And if this is the thickness, if this is the liquid vapor interface, at that point the shear stress would be 0. No slip, no relative velocity at the solid liquid interface, and no shear at the liquid vapor interface. Combination of these two would give you a very clean, neat expression for the velocity, which is a function of the operational parameter, which is u naught, which is a function of the property, which is mu. The h is again the geometric, the operational parameter, which dictates what is going to be the value of h, and as a function of x and so on. So, rho g x and so on. So, another example of how to use shell momentum balance to solve problems of momentum transfer, and in the next class we would see a slightly more different problem.